Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will learn how the MOSFET can be used as an amplifier in the common source configuration. And using the small signal analysis, we will also find the expression of the voltage gain, the input impedance, and the output impedance of the amplifier. Now when the MOSFET is used as an amplifier, then typically it can be used in the three configuration, that is common source, common drain and the common gate configuration. And out of the three configurations, the common source is by far the most popular MOS amplifier configuration. So in this configuration, the small input signal is applied between the gate and the source terminal, while the output is measured between the drain and the source terminal. That means as far as the AC signal is concerned, then the source terminal is common between the input and the output side. And hence, this configuration is known as the common source configuration. Now for any voltage amplifier, the voltage gain, the input and the output impedance are some of the important parameters. And using the small signal analysis, it is possible to find all these parameters. So as we have seen in the previous video, under the small signal approximation, the MOSFET can be replaced by the small signal model. And using this model, it is possible to do a small signal analysis of the given amplifier circuit. Now in the previous video, we have briefly talked about the common source amplifier configuration, where on top of the DC biasing voltage, a small input signal was applied. But practically, this is how the MOSFET is biased. And using the coupling capacitors, the input signal is coupled to the amplifier. So as we have discussed earlier, under the small signal approximation, it is possible to perform the DC and the AC analysis separately. So for the DC analysis, all these capacitors will act as an open circuit. And as you can see, here the MOSFET is biased in the voltage divider biasing configuration. So using the DC analysis, it is possible to set the operating point. Now on top of this DC biasing, a small input signal is applied through the coupling capacitors. So for this AC analysis or for this small signal analysis, all the DC voltage sources in the circuit will act as a 0. While at the operating frequency, the coupling and the bypass capacitors will provide a very low resistance. And for the simplicity, they can be replaced by the short circuit. And then after, the MOSFET will get replaced by the small signal model. That means to perform the AC analysis of any circuit, we need to follow 3 steps. That means first consider all the DC sources in the circuit as 0, and then replace all the coupling and the bypass capacitors by the short circuit. And then after, replace the MOSFET by the small signal model. So here, since the bypass capacitor acts as a short circuit, so this resistor RS will also get short circuited. And if we see the equivalent circuit, then it will look like this. So here, this input signal is appearing between the gate and the ground terminal, or effectively, it will appear between the gate and the source terminal. Similarly, the one end of this resistor R1 and R2 is connected to the gate terminal, while the other end is connected to the ground terminal. That means effectively, these two resistors are connected between the gate and the source terminal. Similarly, this resistor RD will appear between the drain and the source terminal. So if we see the small signal equivalent circuit, then it will look like this. So for this circuit, now let us find the voltage gain, the input impedance and the output impedance. And first of all, let us find the input impedance. So if Vin is the input signal and this In is the input current, then this input impedance is the ratio of this input signal to the input current. Now here, since the gate and the source terminal will act as an open circuit, so this current In will flow through the parallel combination of this R1 and the R2. That means we can say that this input voltage Vin is equal to R1 parallel R2 times In, or we can say that this input impedance, that is Vin divided by In, is equal to R1 parallel R2. So at the low frequencies, the input impedance of this MOSFET is very high, or ideally it is infinite. But because of these external resistors, the input impedance of this configuration is equal to R1 parallel R2. So to achieve the high input impedance, the value of this R1 and R2 should be very high, and preferably it should be in mega ohms. Similarly, now let us find the output impedance. So the output impedance is the Thevenin's equivalent impedance which is seen from the output side. And to find that, we will consider all the independent sources in the circuit as 0. That means we will consider this input signal as 0. Now, since the resistors R1 and R2 are connected in parallel with the input signal, so they will also get short circuited. And once the Vin is 0, then this voltage VGS will also become 0 because the voltage between the gate and the source is equal to the input signal. That means this independent current source will also act as a 0, or we can say that it will act as a open circuit. So in this case, the Thevenin's equivalent impedance which is seen through the output side is equal to RD, or we can say that the output impedance is equal to RD. That means for this amplifier configuration, the output impedance is equal to RD. Alright, so similarly, now let us find the voltage gain. So here, the output is measured between the drain and the source terminal. And since this drain current ID is flowing in this anti-clockwise direction, so we can say that this Vout is equal to minus ID times RD. That is equal to minus Gm times VGS times RD. And as you can see, this voltage VGS is equal to Vin. So from this we can say that this voltage Vout is equal to minus Gm times Vin times RD. That means the voltage gain Vout divided by Vin is equal to minus Gm times RD. So from this expression we can say that by increasing the value of RD, we can increase the gain. But the value of RD cannot be increased indefinitely, because as the value of RD increases, then the voltage drop across this resistor RD will increase, and because of that, the voltage VDS will reduce. So if this voltage drop is too large, then the MOSFET may come out of the saturation, and hence the value of the RD cannot be increased indefinitely. But by cascading multiple such stages, it is possible to increase the voltage gain. Alright, so now so far we have neglected the effect of the channel length modulation, and we have assumed that the output impedance of the MOSFET is infinite. But considering the finite output impedance, this is the small signal equivalent circuit. So as you can see, there is an additional output resistance between the drain and the source terminal. So in this case, the input impedance will remain the same. That means in this case, Zin is equal to R1 parallel R2. But now, this output impedance is the parallel combination of this RO and the RD. That means output impedance is equal to R0 parallel RD. And similarly, the voltage gain AV is equal to minus Gm times this RD parallel RO. So considering the finite output resistance of the MOSFET, these are the expressions of the output impedance and the voltage gain of this amplifier. Alright, so far using this small signal analysis, we found the expression of the voltage gain, the input impedance and the output impedance of this common source amplifier. And here, this amplifier is biased using the voltage divider biasing configuration, right? So as we have seen earlier, in this voltage divider biasing configuration, this source resistor provides the negative feedback and it improves the biasing stability, right? But whenever the bypass capacitor is used, then for the AC signal, it will act as a short circuit. And because of that, it will not have any impact on the AC analysis. But sometimes, to improve the frequency response and to improve the stability of the amplifier, the source resistor is not bypassed. And in that case, this source resistor will also come into the picture during the AC analysis. So because of this source resistor, the voltage gain of this amplifier will reduce. And through the small signal analysis, it will get clear to you. So now let us see the small signal analysis of this common source amplifier when there is also source resistor. So the procedure for the small signal analysis will remain the same. So first of all, we will replace all the coupling capacitors by the short circuit and all the DC sources in the circuit will act as a 0. And then after, we will replace the MOSFET by the small signal model. So the first thing, if you observe, then the source resistor is connected between the source and the ground terminal. And here, the input signal is appearing between the gate and the ground terminal. Similarly, these two resistors R1 and R2 are appearing between the gate and the ground terminal. And this resistor RD is appearing between the drain and the ground terminal. So if you see the equivalent circuit, then the small signal equivalent circuit will look like this. So for this circuit, first of all let us find the voltage gain. Now here, since the drain current ID is flowing in this fashion, so we can say that this output voltage Vout is equal to minus ID times RD. That is equal to minus GM times VGS times RD, right? So now let us find the relationship between this voltage VGS and the input signal. So if you observe over here, then this drain current ID is also flowing through this resistor RS. And let's say because of that, the voltage drop across this resistor is equal to Vs. That means this voltage Vs is equal to ID times Rs. That is equal to Gm times Vgs times Rs. And here the voltage between the gate and the ground terminal is equal to Vin. So if we apply the KVL, then we can say that this input signal Vin is equal to this voltage Vgs plus Vs. That is equal to Vgs plus Gm times Vgs times Rs. That is equal to Vgs times 1 plus Gm times Rs. Or from this we can say that this voltage Vgs is equal to Vin divided by 1 plus Gm times Rs. So in this way, we found the relationship between the voltage Vgs and the input signal. So now let us put the value of Vgs in this expression. That means from this we can say that this output voltage Vout is equal to minus Gm times Rd times Vin divided by 1 plus Gm times Rs. Or we can say that the voltage gain AV, that is Vout divided by Vin, is equal to minus Gm times Rd divided by 1 plus Gm times Rs. So this is the expression of the voltage gain when the source resistor Rs is also present in the amplifier. And whenever this Rs is equal to 0, then the voltage gain is equal to minus Gm times Rd. But because of the presence of this Rs, the voltage gain will reduce. So similarly, now let us find the input impedance. So in this case, the input impedance will remain the same because here the gate to source terminal acts as an open circuit. That means the input current In is flowing through the parallel combination of this R1 and the R2. That means Vin is equal to In times R1 parallel R2. Or we can say that this Vin divided by In, or the input impedance, is equal to R1 parallel R2. So this is the input impedance for the common source amplifier including the source resistor. And similarly, now let us find the output impedance. So as I said, the output impedance is the Thevenin's equivalent impedance which is seen through the output side. And to find that, we will consider all the independent sources in the circuit as 0. That means this input signal will act as a short circuit. And once we consider this Vin as 0, then these two resistors will also get short circuited. And because of that, this voltage VGS is also equal to 0. So let us see how. So if we apply the KVL in this loop, then we can say that voltage VGS plus Vs is equal to 0, where this Vs is the voltage drop across this resistor Rs. And as we have seen, this voltage Vs is equal to Id times Rs. That is equal to Gm times Vgs times Rs. So if you put the value of Vs in this expression, then we can say that Vgs plus Gm times Vgs times Rs is equal to 0. That means VGS times 1 plus GM times RS, that is equal to 0. That means in this case, this voltage VGS is equal to 0. And since the voltage VGS is equal to 0, so this dependent current source will act as a open circuit. And in this case, the Thevenin's equivalent impedance, which is seen through the output side, or Zout, is equal to RD. That means in this case also, the output impedance is equal to RD. So in this way, we found the expression of the input and the output impedance as well as the voltage gain for this common source amplifier when the source resistor is also present. Alright, so now let us take one example so that whatever we have discussed so far will get clear to you. So here, for the given MOS amplifier, we have been asked to find the input impedance, the output impedance and the voltage gain. And here, we have been also given the threshold voltage as well as the device constant for the MOSFET. So for the small signal analysis, we need the value of the transconductance. And to find the value of the transconductance GM, first of all let us do the DC analysis. So for the DC analysis, all the coupling and the bypass capacitors will act as an open circuit. And here, assuming the gate current IG is equal to 0, we can find the voltage VG. So this voltage VG is equal to 10 mega ohm divided by 10 mega ohm plus 40 mega ohm times 30 volt, that is equal to 6 volt. So using the voltage divider rule, we can find the gate voltage VG. And here the current through the source resistor is equal to ID. That means voltage Vs is equal to Rs times ID. That means voltage VGS is equal to 6 volt minus ID times Rs. And here, assuming the MOSFET is operating in the saturation region, this drain current ID can be given as K times VGS minus VT whole square, where this K is the device constant. Or we can say that ID is equal to K times 6 minus ID times Rs minus VT, that is minus 3 whole square. That means drain current ID is equal to 0.4 times 10 to the power minus 3 minus ID times Rs whole square. Or we can say that 2500 ID is equal to 9 minus 6 times ID times Rs plus ID square Rs square. Now here the value of Rs is equal to 1.2 kilo ohm. So if we put the value of Rs in this expression, then we can say that 1.44 times 10 to the power 6 times ID square minus 9700 times ID plus 9 is equal to 0. So if we solve this quadratic equation, then we will get the two roots. First root is 5.62 milliampere, while the second root is 1.11 milliampere. Now if we take the value of ID as 5.62 milliampere, then the MOSFET will not operate in the saturation region. That means the value of the ID should be equal to 1.11 milliampere. And with this value of the drain current, the voltage VGS will be equal to VG minus Vs, that is equal to 6 volt minus ID times Rs, that is equal to 6 minus 1.2 kilo ohm times 1.11 milliampere, that is equal to 4.668 volt. And the transconductance GM can be given as 2 times K times VGS minus VT, that is equal to 0.8 times 10 to the power minus 3 times 4.668 minus 3, that is equal to 1.33 millisiemens. So in this way, we got the value of the transconductance. And once we know the value of the transconductance, then using the small signal analysis, we can find the value of the required parameters. So for the AC analysis, we can consider all the coupling capacitors as the short circuit, and we can replace all the DC sources in the circuit as 0. And then after, we can replace the MOSFET by the small signal model. So if we see the equivalent circuit, then it will look like this. So as we have seen, in this case, the input impedance is the parallel combination of this R1 and the R2. That means in this case, it is the parallel combination of this 10 mega ohm resistor and the 40 mega ohm resistor. That is equal to 8 mega ohm. That means the input impedance of this amplifier configuration is equal to 8 mega ohm. Similarly, the output impedance is equal to RD, and in this case it is equal to 3.3 kilo ohm, and the voltage gain is equal to minus Gm times RD, or in this case it is equal to minus 1.33 millisiemens times 3.3 kilo ohm. That is equal to minus 4.43. So this is the voltage gain of this amplifier. So in this way, using this small signal analysis, we can find the different amplifier parameters. So in this video, we have done the small signal analysis of this common source amplifier whenever it is biased using the voltage divider biasing configuration, right? Similarly, another popular biasing configuration for the MOSFET is the drain feedback bias. So similarly, in the next video, we will see the small signal analysis of this common source amplifier when the MOSFET is biased using the drain feedback bias. But I hope in this video, you understood the small signal analysis of this common source amplifier. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.